Okay, the last section we're going to cover is 9.3, is on page 639. It talks about separable equations. This is a first order differential equation that can be written in this form. So if I can separate the g from the f, which means I could somehow get some function of y dy equal some function of x dx and integrate, then I could solve for y. That's the idea. Separable equation is one form of a differential equations, which is our traditional calculus. This is on page 645, and directions solve the differential equation. Now, I didn't go over what differential equation is because we really don't need to know that in full details. We just need to know that a separable differential equation is an equation that fits our calculus 5A and 5B courses. That is, if I cross multiply here, divide by radical y, so I'm trying to solve for y, if I could. And then I can integrate. This is y to the negative 1/2, add 1 to the power, divide by that, x squared over 2 plus c, and that would mean square root of y will equal x squared over 4 plus c, and y would equal x squared over 4 plus c quantity squared. And that would be my final answer. And what this says, take a derivative of that, put it on one side, take x times the square root of y, you should get the same thing. That's what that means. On number 4, the same idea applies. I'm glancing at this and thinking this is dy dx equals negative x e to the y. So dy over e to the y equal negative x dx. I was able to separate those. I integrate. That's e to the negative y over y. The e to the negative y over negative 1 equal negative x squared plus c. So 1 over e to the y equals x squared plus c. That means e to the y equal 1 over x squared plus c, and y equal natural log of 1 over x squared plus c. If they give me initial conditions, I figure out what c is. Otherwise, that's pretty much it. And this problem, again, if I think of this as dz equal negative e to the t plus z is e to the t times e to the z. When you multiply terms with the same base, you add their powers, divide by e to the z both sides, and there it is. And once I separate, pretty much calculus, negative e to the negative z equal negative e to the t plus c. So that becomes a positive. And 1 over, so e to the z will equal 1 over e to the t plus c. And z will equal natural log of 1 over e to the t plus c. Of course, you could use properties of logs if you want and say that's natural log of 1, which is 0, minus natural log of e to the z plus c. Whatever works. If they gave me initial conditions, that would mean I would have to find c. Looking at number 12, I'm going to do that a couple of different ways. So if I cross multiply, if I let u equal x, du is dx, and dv equal the sine of x dx, so v is the integral of that, but make it negative cosine of x. So y squared over 2 will equal u times v minus the integral of v du. So y squared over 2 would equal negative x cosine of x plus the sine of x plus c. Now I want to work this out two different ways. One way, I want to go ahead and say, okay, as is, I'm going to take this, let me see, here. Case 1, I'm going to say y squared equal negative 2x the cosine of x plus 2 the sine of x plus c. I'm gonna say when you multiply c by 2, it's gonna be absorbed. Or I'm gonna say y squared is gonna equal negative 2x the cosine of x plus twice sine of x plus 2c. Just to show you that it doesn't really matter and no need to tackle c. C plus a number is c, c minus a number is c, c divided by 5 is c. Keep it like that, saves you a lot of work. And this says y equal plus or minus negative 2x the cosine of x plus twice the sine of x plus c. Now, they gave me initial conditions. Y of 0. This is very important in differential equations. That's a 0. That's a 0. That's a c. And that equals a negative 1. What does that mean? That means the positive is not allowed. The only way this could have a solution if you could have negative a radical equal a negative, because a square root can never be negative. And if you square both sides, you get 1. Plug 1 in there. And this tells me that y equals negative the square root of negative 2x the cosine of x plus twice the sine of x minus 1 is the solution of this differential equation satisfying this initial condition. If I was to use 2c when I simplified that 2 right there, then I was going to say y equal plus or minus, so the work is the same. But students often ask, what happened to the 2? How come you're not multiplying the c by that? Well, it doesn't matter. I'll show you. So y of 0, again, this is plus or minus the square root of 0 plus 0 plus 2c, and that equals a negative 1. Negative square root of 2c must equal a negative 1, otherwise there's no solution. So square root of 2c equal a 1. Square both sides, c equal 1/2. And what happens when you put 1/2 in there? Oh, that was a plus, right? So there, does it matter? It really makes no difference. It's the same regardless. So might as well just keep it as c, and that saves you some pain on the long run. Some. And I wanted to do one more. Yeah, let me do it. That's okay. Now there are a couple of applications in this section that I haven't touched on yet. But here we are. This is a separable equation. Again, this says if I move this to the other side, I will get 3y squared square root of x squared plus 1 dy equals negative x dx. And if I divide by the 3, well, actually I could leave the 3 here because I could see it cancels out. That will make life easier. It doesn't really matter because you're going to divide by both sides and you're going to cancel out. If I integrate, I'm going to get y cubed to equal, and this, I'm going to let u equal x squared plus 1, du is 2x dx. So this is negative 1/2. The integral of u to the negative 1/2, right? So this says y cubed equal negative 1/2. Add 1 to the power, divide by that. Y cubed equals negative the square root of x squared plus c plus x squared plus 1 plus c. And y would equal, now I could find u right now, since it's an even, not, since it's an odd power. and y would equal the cube root of 2 minus the square root of x squared plus 1 would be the solution. Now we are going to stop here. Again, there are a couple of applications I would really like to touch on, but this is as far as we're going to go. And your homework is 9 through 17.